And Professor Clements with you in Chapter 31 of OpenStax College Physics, minus my little video insert today. But talking about half-life and activity, Section 5, binding energy, Section 6, and the tunneling, the fun explanation of alpha particle decay, Section 7. So half-life, you've probably heard of the word half-life. It tells us the characteristic time for the number of radioactive nuclei to decrease by a factor of 2, to go down to half. So here we have some radioactive isotope. Start with 1,000 times 10 to the third, and time equals 0. After one half-life, we're down to 500. In one more half-life, we're down to 250. In one more half-life, we're down to 125. Each time we're dividing by 2 to produce that, and they have a chart over here that takes us out quite a ways on the number of half-lives. But in radioactive decay, the individual nucleus has some probability of decaying. We don't know when that's going to happen. The half-life may be 100 years, but the nucleus may decay in 10 minutes. On the overall sample, statistically, there is this half-life time that's reliable because we have great numbers of nuclei present. So we do have this characteristic half-life time when we're talking about a whole sample. We cannot apply this to just one nucleus or a handful of nuclei, 12 nuclei. But when we get into the billions and trillions of nuclei in realistic samples, then this law is true. We'll get this exponential decay. An exponential decay. It's not linear, but it's an exponential, and we'll see the calculation for it in a little bit. So we have this probability the nucleus will decay in a whole assembly of nuclei, a large number of nuclei. They decay following this half-life rule. In one half-life, whatever that may be, it's 55 minutes, maybe it's 54 minutes. But in 54 minutes, half of the nuclei would decay. Another 54 minutes, another half would decay, and so forth. Or it might be 20 minutes for the half-life. So after the start time, 20 minutes, let's say we have 500 nuclei. Another 20 minutes, 250. Another 20 minutes, 125. How much total time has elapsed if the half-life is 20 minutes? So 1 hour, 20, 20, 20, 60 minutes. But to go from one time, whatever time that is, to the next, if the time is one half-life, then the number of nuclei decrease by a factor of 2. So you ought to try making your own definition for half-life. Write out what you think half-life is. And a question, do you think the mass is disappearing? So if we have 1,000 times 10 to the third carbon-14 atoms, do you think at this point half of the mass has disappeared, and now 3/4 of the mass has disappeared, and 7/8 of the mass has disappeared? Do you think that's the case? And the answer is no. The carbon-14 changes, I think, to nitrogen. I have to look that up. But we're just losing a little bit of mass as the decay occurs. As the nuclei changes from one thing to another, that mass becomes energy of the alpha, beta, or gamma particle that's emitted. But we're not losing half the mass and half again and half again. The radioactive isotope decays to some other daughter product, as we talked about earlier. So the half-life, length of time required for 1/2 of the original nuclei to decay. This is the law for half-lives. We have our number of nuclei, capital N, at any time t, being equal to the number of nuclei at time equals 0, multiplied by Euler's number, E, to the minus lambda t power. So you have an e to the x key on your calculator. You're going to get to make use of it in this chapter. Lambda is called the decay constant. Lambda is equal to 0.693 divided by t 1/2. So you might try a little numerical experiment on your calculator. Suppose the half-life is 20 minutes. Put in 20 minutes here, and put in 20 minutes for the t up here. I hope right now you'll realize you're going to end up with e to the minus 0.693. Try evaluating e to the minus 0.693 on your calculator and see what you get, and see if you're surprised or you say eureka. So at n is equal to n naught at time equals 0. Whatever time you want to start, call that time equals 0. You have a certain count of radioactive nuclei. Then the activity, and our textbook uses R for the activity. Older books you'll find an A, which is a little bit confusing because A we're using for the atomic mass number. But so we'll use R. R is the activity. R can be calculated by lambda times n, the decay constant times the number of nuclei. This will tell us how active, how dangerous a radioactive sample is, how many decays per second are occurring. Because n is very often a very large number, it's convenient to measure activity in the unit of the Curie, named after the Curies who around 1900 worked with radioactivity. So 1 Curie is 3.7 times 10 to the 10th decays per second. That's 37 billion decays per second. And the typical radioactive sources that a school might have would be in the microcurie range. A 1 Curie source is dangerous. You'd need to have special licensing to have one of those sources. But 1 Curie, 3.7 times 10 to the 10th decays per second. We'll use that conversion factor in some sample problems in class. Is it true that the activity obeys this exponential relationship? Can we say that the activity R at some later time is equal to the activity at time equals 0 multiplied by e to the minus lambda t? And you should be saying yes. If I put in what R is can be replaced by lambda times n, I'd have lambda n on the left, I'd have lambda times n naught over here, the two lambdas would cancel, and I'd get back to this n equals n naught e to the minus lambda t. So we can do the calculation for the number of particles, or we can do the calculation for the activity. So this radioactive law that we have this regular decay, this exponential decay, can be used for radioactive dating. Radioactive dating. If you can measure, say, how many carbon-14 isotopes, how many of those nuclei are present in a piece of cloth, and you assume that the original number of carbon-14 nuclei is the same as today in our environment, then you could calculate the age of something like the Shroud of Turin. Or archaeologists make use of this all the time. You can calculate the age of something that has organic material using carbon-14 dating methods. Carbon-14 has a known half-life. If we measure how much carbon-14 remains in the sample that is not decayed yet, and assume we know the original amount of carbon-14, assume it's the same as today, then we can calculate the age. Carbon-14 dating has been calibrated by counting tree rings data back for thousands of years. There are some old trees, there's some fossilized trees, and the width of the tree rings depends on the weather. So that tree ring timeline can be taken way back, and carbon-14 dating has been verified. So read up on that and ask me questions if you have questions. The Earth is warmer than it should be if it's 4.5 billion years old, and the thinking is that there's radioactive decay occurring in the core of the Earth that is releasing energy and keeping the Earth warmer than what it otherwise would be. The radioactive isotopes inside the core of the Earth. So I hope that answers some questions you have on radioactive dating. Again, we'll do some example calculations in class, and I'll have some example videos posted in a couple of days. If you're watching this the same day I record this. So suppose you were given, let's come back here just a little bit. Suppose you were given a radioactive source and you're holding it in your hand. How would you tell if it was dangerous or not? How could you, what would you have to know to decide if your sample was dangerous to you? Well, a dangerous sample has a high level of radioactivity. So what would be true about the half-life that would give us a big number for lambda? And we see that if the half-life is small, then lambda will be large. So if your radioactive isotope has a short half-life, meaning a lot of the decays happen in a short amount of time, that will make it dangerous. Or if you have a lot of nuclei present, if you have several grams of the radioactive isotope versus a microgram, that would make the material hazardous. But the activity gets higher, the material is more dangerous if the half-life is shorter and the number of nuclei is greater. And by dangerous I mean at the immediate time when you're holding the sample. Waste material from nuclear power plants is dangerous because there's a big N and the lambda can be small, but that means it's going to last a long time and be dangerous for a long time if the half-life is long. But just holding something in your hand, you want to avoid holding something that has short half-life and has a lot of particles in the material. So don't do that. So let's go on here with binding energy. Binding energy. We've talked about ionizing an atom, removing an electron from an atom, a few electron volts needed. Do you think we can remove protons and neutrons from the nucleus? And the answer is true. If we add energy to the nucleus, theoretically, we can separate the protons and neutrons. This is a little bit more of an academic exercise than a practical exercise. We want to get an idea of how tightly bound protons and neutrons are to each other in the nucleus. So to do that, we calculate something called the binding energy. So here's kind of a concept of what happens. Somehow we apply a force for a certain distance. We do work on the proton or neutron and separate them all out. This is really an abstract type of view here. Just saying that it is going to take some energy to separate the protons and the neutrons. They're held together with a strong nuclear force, and to separate them, theoretically, hypothetically, we can do so by calculating how much energy would we have to free up all the protons and the electrons. This bound system has less mass than the mass of the separate protons and neutrons. So there's less mass in the nucleus when it's assembled than there is in the separate protons and neutrons. You might be thinking E equals mc squared, I hope. And if we supply some energy, we can create some mass and get the particles separated. So that's the overall concept. To calculate this total binding energy for the nucleus, we need to first take a look at the isotope symbols, the Z and the A, the atomic mass number. Do a subtraction. That'll tell us the number of neutrons that are present. So carbon-14, 6 protons. Carbon-14, the atomic mass number is 14. 14 minus 6 is 8. So 6 protons, 8 neutrons. When we separate them out, the masses that are given are for neutral hydrogen atoms. In the tables you'll find. So the mass of carbon-14 would include the electrons. And the electron mass is not ignorable. We need to keep track of it. So when we separate the protons and the neutrons out, we'll let each proton take along one electron and form a neutral hydrogen atom. So the neutral hydrogen atoms, that will be the same as our count of protons in the nucleus. And there's a table that has the mass of a neutral hydrogen atom in U's, the atomic mass unit. It's much more convenient than kilograms. So we'll have protons. We take 6 in my verbal example here with carbon-14, 6 times the mass of one neutral hydrogen atom, and we take 8 times the mass of one neutron. Again, the neutron has a mass you look up in a table. So we'd total those, that total mass, then we would subtract the mass of the nucleus, and we would come up with some mass difference. Again, there's more mass when we have the separate particles, less mass in the nucleus. So we'd subtract the mass of the nucleus from these separate masses, all added up. We get some U value. It'll be a small number, less than 1. We multiply by 931.5 MeVs per U's, and we found the total binding energy for the nucleus. The total binding energy for the nucleus. Many times we would like to know the binding energy per nucleon. This will allow us to compare one isotope to another isotope on a level playing field. If we have a big nucleus, it's going to have a big binding energy, total binding energy. If we have a small nucleus, it'll have a small total binding energy. But binding energy per nucleon gives us a better basis to compare isotopes. So all we do is we've done the work here in steps 1 through 4 for the total binding energy. We divide by the number of nucleons. For carbon-14, what is that number? Is it 6, the count of protons? Is it 8, the count of neutrons? Is it 14, the atomic mass number? It's 14. 14 is the number of protons and neutrons combined. It's the number of nucleons. So whatever number we get, divide by 14, that's the binding energy per nucleon for carbon-14. Here's a graph across the periodic table of binding energy per nucleon. And you might have to look at the textbook and get a little bigger version of this. But binding energy per nucleon, that's in MeVs on the vertical scale. And atomic mass, the A value across to the right. So uranium is clear out on the end here, and hydrogen back here. Well, take a look. We get a little peak here for helium nucleus, the 2 protons and 2 neutrons. That has, compared to the neighboring elements around it, it has a very stable configuration. It's a high binding energy per nucleon. And as we go across the table here, or the graph here, we find that iron is at the peak of this binding energy per nucleon curve. Iron is the most stable nucleus. This does not make iron strong. That's a chemical property. But iron requires the most energy per nucleon to free things up. When we talk about nuclear energy, we're going to find that energy is released in a nuclear reaction if the fission occurs, and we split uranium and the daughter products are in here, or if we have fusion, fusing hydrogen to form helium. As we head towards the peak of this curve, energy is released. And the small peaks in here, that's where we have an unusually stable nucleus, and a little bit like the noble gases, the protons and neutrons are in a shell configuration. So let's go a little further here. Alpha particle decay. How does an alpha particle get out of the nucleus? Well, imagine a marble rolling in a bowl here, and the marble does not have enough energy to go higher than this dashed line. That's where its potential energy is all potential energy. Kinetic energy is 0. But in classical physics, in order to get over the peak, it would have to have more energy to get out. The alpha particle is able to escape from the nucleus without having enough energy to get out. It's as if the alpha particle went through a tunnel and then found itself outside the nucleus, and the electrical repelling force would make it speed up like it's going downhill off of this cone. So here is more the nuclear physics diagram of this, potential energy graphed here vertically, and the strong nuclear force forms a potential energy barrier where the particle would have to have this much energy to get out. The alpha particles inside the nucleus, so you can calculate their energies, and they do not have enough energy to get over the hump here. They don't have enough energy to make it out. So they just kind of bounce around inside the nucleus billions upon trillions of time. As they do so, quantum mechanics tells us that there's some non-zero probability that the alpha particle will get out here. How's it going to do that? Well, let's think about the energy of the alpha particle. At any time, the energy is the kinetic energy of the alpha plus the potential energy of the alpha. Suppose that the kinetic energy went negative. If the kinetic energy went negative, then we could have a situation where the potential energy would be bigger than what we expect on this dashed line. So kinetic energy negative, potential energy gets bigger, and this thing can get out of the nucleus if the kinetic energy can be negative in this realm. Well, quantum mechanics allows for this. So here would be the wave function that helps us find particles. Don't need to know too much about that. Here we have the wave function of the alpha particle outside, so it's been escaping with some probability. Inside we have, and this is the barrier set up by the strong nuclear force. Inside here we have an exponential decay of the probability of finding the alpha particle, but for our purposes, more important to talk about is Heisenberg uncertainty principle. Uncertainty in the energy times an uncertainty in time equals h divided by 4 pi. And if we have a brief time here, if delta t is small, then delta E can be large, and the kinetic energy can go negative for a short time. So kinetic energy being negative in here for a short time, that's not disallowed by quantum mechanics. Kinetic energy, 1/2 mv squared, mass is positive, v squared is positive, but quantum mechanics says that the alpha particle has a negative kinetic energy for a brief time. That allows the particle to have more potential energy than this potential barrier and can get out. And now when it's out here, the alpha particle is then repelled by the Coulomb force, and the alpha particle continues on its way. So that's the explanation for quantum, for tunneling, alpha particle decay. This is in agreement with experiments. The equations of quantum mechanics give us a prediction that matches what we see for various radioactive nuclei that emit alpha particles. So highly unusual. It's definitely not classical physics, but the kinetic energy being negative allows the potential energy to be high enough that the alpha particle gets across this barrier. It's not really going up here. It's tunneling through the barrier. So quantum mechanical tunneling. Some other things you might want to be interested in for Chapter 31 is that we have investigation of the isotopes. All the isotopes greater than Z of 83 are radioactive. No stable isotope. And there are 2 elements lower in the periodic table with Z less than or equal to 83 that have no stable isotopes. Scientists have identified about 280 stable isotopes and over 800 radioactive isotopes. That's a little trivia. Don't have to memorize those numbers for my class. This is Professor Clements asking you to keep reading and asking questions.